Welcome, Eleanor. Today we're diving into a crucial topic, AI's material footprint, from atoms to algorithms. It's vital to understand the physical reality behind AI's digital facade, from the mineral extraction required to its immense energy demands.
Thank you, Elliot. I'm really keen to grasp this better. I think understanding the tangible impact of AI, especially regarding sustainability and ethical dimensions, is incredibly important right now.
Precisely. We'll explore how AI's role fits into our shared material world, and then move into the ethical considerations of its footprint, ultimately aiming towards more sustainable AI practices. Eleanor, let's begin our discussion on the material reality of AI, focusing on its journey from mineral extraction to energy consumption. We'll start with the foundational elements, the raw materials.
Understood, Elliot. So, what specific minerals are we talking about, and how does their extraction directly relate to AI's physical presence?
A prime example is cobalt. It begins as an atom forged in stars, then extracted from the Earth, often in challenging conditions, to become a critical component in lithium-ion batteries. These batteries power the devices and data centers essential for AI operations.
So, cobalt and lithium are key. This highlights a direct link between natural resources and technological advancement. Does this extraction process also involve significant human labor considerations?
Yes, absolutely. The extractive systems for materials like lithium and cobalt frequently exploit human labor, often under dangerous and unethical conditions. This underscores the shared materiality where human and non-human entities are deeply entangled.
I see. So, the material reality of AI starts with the physical extraction of minerals like cobalt and lithium, often with significant human and environmental costs, forming the basis of its hardware. What's the next major material consideration after extraction?
Precisely. The next critical aspect is energy consumption. AI's development and operation are deeply tied to substantial energy demands, which enable and constrain its capacities.
How significant is AI's energy consumption? Are we talking about a measurable impact on global energy use?
Indeed, projections suggest AI's energy consumption could surpass the annual consumption of small nations. This significant demand contributes to a substantial carbon footprint, compounded by the energy required for specialized hardware production and data center construction.
That's a considerable impact. Are there efforts underway to mitigate this energy demand, perhaps through more efficient hardware or software?
Yes. Efforts are focused on developing energy-efficient hardware and optimizing neural network architectures to reduce power consumption. OpenAI CEO Sam Altman has also highlighted the critical need for advancements in clean energy to support AI sustainably.
So, AI's material reality involves not only the extraction of minerals, but also immense energy consumption, with efforts to improve efficiency and a recognized need for clean energy sources. How does this connect to broader climate and ecological thinking?
AI's environmental impact is part of a broader existential threat stemming from systemic behaviors that lead to environmental degradation. Reframing our relationship with non-human entities is essential for achieving sustainable outcomes.
What does reframing our relationship with non-human entities entail in the context of AI's material footprint?
It means viewing AI not as an isolated digital entity, but as an integral part of a broader material system. This perspective allows us to design AI systems that influence and promote sustainable practices, acknowledging its deep entanglement with the natural world.
So, AI's material reality extends beyond its immediate hardware and energy use to its role within a larger ecological system. What challenges and opportunities arise from this understanding in AI development?
AI technologies often reflect and exacerbate existing inequalities in access to resources and expertise. The reliance on large-scale datasets can also marginalize diverse perspectives, limiting inclusive innovation.
Given these challenges, what are the opportunities for addressing these disparities and fostering more equitable AI development?
Opportunities lie in diversifying training datasets to include broader perspectives and fostering equitable participation globally. This ensures AI development benefits a wider range of communities and aligns with ethical and ecological responsibility.
To summarize, the material reality of AI encompasses the entire life cycle, from the mineral extraction of cobalt and lithium, often with ethical concerns, to its significant energy consumption and carbon footprint. It's also deeply intertwined with broader ecological systems, requiring us to address inequalities and pursue sustainable, equitable development.
That is an excellent summary, Eleanor. Understanding these material foundations is crucial for developing AI responsibly and ensuring its future aligns with ecological and social well-being. Welcome back, Eleanor. We have discussed AI's material reality, from mineral extraction to energy consumption. Now, we will delve into reframing AI's role within our shared material world, moving beyond a purely environmental impact perspective.
Understood, Elliot. So we're shifting from the what of AI's material footprint to the how and why of its integration into our broader reality.
Precisely. This reframing involves recognizing AI as an active participant within a shared material reality. This leads to more realistic ways of conceptualizing AI, aligning our practices with ecological thinking.
What are the philosophical underpinnings of this perspective? Are there specific thinkers who inform this view of AI as an active participant?
Yes, several. Gilbert Simondon, for instance, posits that all entities, living and non-living, emerge through individuation from a shared pre-individual state of potentiality. This suggests a relational understanding of being.
So Simondon's idea implies AI isn't a separate, isolated entity, but rather emerges from and is connected to a broader shared potentiality.
That is correct. Building on this, Donna Haraway challenges artificial divisions between humans, animals, and machines. She proposes co-constitutive relationships, emphasizing their inherent interconnectedness.
And how does Jane Bennett's concept of thing power fit into this reframing?
Bennett's thing power suggests that non-human entities possess a form of agency. This challenges the traditional dichotomy between active humans and passive matter, granting a degree of agency to AI within the material world.
So these philosophical perspectives collectively argue for viewing AI not as a tool separate from us, but as an interconnected, active entity within a shared material reality, possessing a form of agency?
That is an accurate summary of the philosophical shift. Now, let us consider how this reframing impacts AI's role in design and architecture, specifically its material interactions.
I'm interested in this. How does AI's material agency manifest in fields like architectural design?
The predominance of image-based AI in architectural design highlights a tension between structure and representation. However, geometry-based AI systems are now emerging, extending material processes.
Could you elaborate on extending material processes with geometry-based AI? What does that practically mean?
Certainly. Generative 3D geometry AI models, such as Trellis and Trippo AI, draw on large data sets to infer and reconstruct beyond mapped physical artifacts. They can generate new forms and structures that extend the possibilities of material realization.
So these AI systems aren't just replicating existing designs, but actively contributing to the creation of new material forms and structures, almost like a co-designer?
Precisely. The integration of image and geometry in architectural AI offers innovative potential. It moves beyond self-referential systems that merely reinforce existing patterns towards co-creating new systems of meaning and interaction.
This implies AI can be an agent in shaping our built environment in novel ways, moving beyond just digital representation to influencing physical outcomes.
Indeed, this leads us to the future directions and challenges of this reframed understanding. AI could evolve into an agent of material transformation, contributing to a future of material equity.
What are the primary challenges in designing AI systems that align with this vision of material equity and ethical responsibility?
The core challenge lies in moving beyond self-referential systems that reinforce existing patterns. We must design models that actively co-create new systems of meaning and interaction, ensuring their contributions are sustainable and equitable.
So, reframing AI's role means acknowledging its philosophical interconnectedness and agency, leveraging its capacity for material transformation in design, and ensuring future development prioritizes ethical, sustainable, and equitable outcomes, moving beyond mere replication.
That is an excellent and comprehensive summary, Eleanor. Understanding these dimensions is fundamental for responsible AI development. Welcome back, Eleanor. Having established AI's material reality and its reframed role within our shared material world, we now turn to the ethical dimensions of its footprint.
Understood, Elliot. So we're moving from the physical and philosophical aspects to the moral implications of AI's material demands?
Precisely. We will begin by examining the direct ethical challenges arising from material extraction and energy consumption. These are foundational to understanding AI's broader impact.
What are the primary ethical concerns associated with the extraction of raw materials for AI infrastructure?
The extraction of critical materials, such as lithium and cobalt, frequently involves human labor exploitation. Workers often operate under dangerous and unethical conditions, raising significant social justice issues.
And how does this extraction process impact the environment?
Beyond labor, these processes contribute to environmental degradation and resource depletion. This directly affects ecosystems and local communities, highlighting the interconnectedness of human and non-human entities.
So, the material sourcing for AI has both human rights and environmental costs. What about the ethical implications of AI's energy consumption?
AI's energy demands are substantial. Projections indicate its consumption could exceed that of small nations, contributing significantly to carbon emissions. This is compounded by the energy required for specialized hardware production and data center construction.
This suggests that technological solutions for AI's energy needs must also consider social justice and equity, not just energy production itself.
That is correct. Energy production alone is insufficient. The ethical framework must encompass how energy is sourced and its equitable distribution. Now, let's transition to how AI technologies themselves reflect and exacerbate existing inequalities.
How do AI technologies perpetuate or amplify existing societal inequalities?
AI development often concentrates high costs and specialized expertise in well-resourced areas. This creates a disparity in access and benefits, limiting participation from diverse global communities.
And what about the data used to train these AI models?
The reliance on Western-centric datasets is a significant issue. It marginalizes diverse perspectives, leading to AI systems that may not be inclusive or relevant to a global user base, thereby limiting inclusive innovation.
So, addressing these disparities would involve diversifying training datasets and fostering broader participation?
Precisely. Diversifying datasets and promoting equitable global participation are crucial steps to ensure AI development benefits a wider range of communities and aligns with ethical responsibilities.
Beyond these foundational issues, what are the broader ethical challenges that AI's development presents?
The broader ethical landscape includes concerns such as authorship in creative works, cultural bias embedded in algorithms, the spread of misinformation, and the overarching environmental impact we've discussed.
Given these challenges, what is the responsibility of fields like design and architecture in engaging with AI ethically?
Design disciplines have a critical responsibility to engage with AI's power and implications. This involves promoting ethical awareness, critically assessing AI's societal role, and advocating for its responsible development and application.
To summarize, the ethical dimensions of AI's material footprint encompass human labor exploitation and environmental degradation during mineral extraction, significant energy consumption with its carbon footprint, and the perpetuation of inequalities through concentrated expertise and biased datasets. Addressing these requires diversifying data, fostering global participation, and critical engagement from design disciplines to promote ethical awareness.
That is an excellent and comprehensive summary, Eleanor. Understanding these ethical dimensions is paramount for guiding AI development towards a more just and sustainable future. All right, Eleanor, we've covered a lot today. We started with AI's tangible material reality, from mineral extraction and energy consumption, then reframed its role as an active participant in our shared material world, and finally delved into the crucial ethical dimensions of its footprint. For your studies, I'd suggest focusing on the interconnectedness of these three pillars. Try to trace the life cycle of a single AI component, like a microchip, from its raw materials to its energy use, and then consider the ethical implications at each stage. This will help solidify the concepts.
That's a great approach, Elliot. I'll definitely use that framework to review the material. Understanding the full life cycle and the philosophical underpinnings of AI's agency especially feels much clearer now.
Excellent. Next session, we'll move into the practical side, exploring concrete strategies and policies for achieving more sustainable and equitable AI practices. We'll look at how we can move forward responsibly.